Hi, this is going to be lecture 21 on the principle of superposition. So here's the basic question that I want to answer in this lecture. Imagine I have a string and I make some kind of shape. You imagine I have my hand here and I wiggle it up and down and I create a shape that travels along the string. Maybe I get a sort of square-ish shape. Hard to do in real life, but it's a good example to use. Somebody else on the other end does the same thing, and maybe they sort of go down, back up, and they make this sort of triangular shape here. So my rectangular shape is going to go this way. The triangular shape is going to go this way. Could be any other shape, of course. I'm going to stick with those because they're simple. Well, what is going to happen when they collide, meet? That's what I'm going to answer here. And that's going to be the foundation, this idea of superposition. You've got more than one wave, more than one impulse on top of each other. Like, what happens? That's going to be the foundation of a lot of really fun physical phenomena. So here's how I'm going to try to track this. I'm going to color this shape blue. I'm going to color this shape green. And so we can keep track of them. And then let's see what happens. Okay, so we can imagine what happens first is that they're just going to get closer and closer until they essentially touch. Those two shapes, they're going to reach each other, and until then, things aren't very interesting. I'm going to assume the whole time, of course, that these displacements from the string, they're small, not like hugely like far out, so that the string doesn't stretch significantly. But then what happens? So they're traveling opposite directions, they're traveling at the same speed. They have to by the wave equation. The wave equation says you can only have one speed on a string. And then I sort of want to draw them like this, but that does not make any sense, right? Because the string, the physical string, can only be in one place at a time. So the string that belongs here, is it up there or is it down there? It can only be in one place. So what actually happens, and that is the key piece of understanding, is that the displacements add. So what that means is I'm going to add the, say, positive displacement here to the negative displacement here. So what does that look like? Well, right at this point, let me use my red pen to show the actual shape of the string. So here, so because left and right just flat, right? Here, it's just the blue one. Nothing interesting happens until around there. Then the blue one, right, the square, the rectangular shape traveling to the right, adds, maybe 1 centimeter plus. The green one starts at 0, but then it subtracts, so it's negative. It's a negative displacement, downwards displacement. So if I add this plus this, right, so this point here plus this point here, means I'm probably going to hit 0 somewhere here. It's going to do this. Now, what happens here? At this point, I reach the end of the blue one. Means I only have the green one left. So it goes down, and now it's just the green one the whole way to the end. Right. So this looks funny, right? What is this? It's the way to calculate it. If I had an actual function, I'd say, okay, I take this is plus 2, 2 centimeters up, minus 1, displacement plus 2, minus 1 makes plus 1 here. Right, so at each point, at each value of x, if x, measures the points along our string, I look what's the displacement of due to the blue shape, I add to the displacement to the green shape, and the result is going to look like this, right? Just blue, then I've got the blue up here, but an increasingly negative green one. That means I get this same slope as the green one here, and then the blue one stops, so now it's just the green one left. It looks like this. Let's go on and see what happens next. So I've drawn the next picture here. blue one is moved a bit over, the green one is moved a bit over, right? The green one's still going left, the blue one's still going right. So now I drew it so that where the blue one ends right in the middle of the green one, where the green one is the biggest displacement. So the combined one, the actual shape of the string would look like this. Up to here, it's just blue, no green displacement. Then I'm adding them together, so now I'm adding this increasing negative one to my blue one. It goes down like this. The green one is a bit taller than the blue one. The blue one's wider. So right here, like -3 plus 2, so it's going to be at -1. Then the blue one stops. So now it's just the green one again. Where the shape of the string would, for an instant, look like this. Again, these very sort of hard corners, of course, is unrealistic. If you actually try to do this on a string, you probably have more rounded shapes. But the principle is the same. Okay, let's go to the next one. Here we are. So a little bit later, the blue one is moved further over. I didn't quite draw this right? It should be like, I drew it kind of bigger than before. Of course, really, this end should be a bit further over, so just this whole thing shifted right. The green one, meanwhile, has moved to the left. Let's add them up. So in this case, the green one is now all the way like inside the range of where the blue one is. But there's a little bit of a gap here, so I guess initially it goes up, then it goes over. Now we'll be hitting the green one, so now we're going down. Now we're here, now we go back up. And then there's still some blue one left. So this is going to be the shape of the string, right? And of course, left, right, it's just flat. Okay, now maybe, pause the video here and draw yourself another picture or two of the kind of situations that's going to happen within the next fraction of a second. So here we are. Here are two more pictures. I got a bit desperate here, squeezing them all onto one page. But hopefully you got the idea by now. So the green one keeps going left, so eventually it sort of comes out on the other side of the blue one. The blue one's going to the right. Still, I just add the displacements to find the actual displacement of the string. So here it's just green now, then comes the blue one starts, the green one goes back, and then it's just the blue one at the end. There. Bit poorly drawn. The red one should of course reach the blue one right where the green one stops. Right. It's badly drawn. Let me fudge it a bit. There, fudged. And then eventually, I could draw more intermediate pictures, of course, but eventually the green one's just going to come out the other side, the blue one's comes out the other side, and then it's going to continue as if nothing has happened. So those two pulses, they just pass through each other. They don't bounce off each other. They don't do much to each other, right? They just pass through each other. But while they pass through each other, the actual shape of the string is the sum of their individual displacements. And it can get these sort of funny shapes. Yes, realistically, it's going to be more rounded than this. But it's going to have some sort of shape that is a combination of the two in lots of different ways as they're passing through each other. And eventually, you're going to end up, like this again. The way they started, except now they're on each other's side. And that's what we call the principle of superposition. That the displacement of individual waves, it doesn't matter whether they're pulses like I've drawn it here, or continuous waves, the individual displacements add. So let's write that down. So let me then state this principle of superposition explicitly. As we said, the actual displacement of the string, of the surface of the water, or the electric and magnetic field in a electromagnetic wave, whatever the displacement is that moves, in which the wave happens, that is the sum of the individual displacements due to each wave it contributes. So in our case, just now, that example, it was the square pulse and the triangular one, where they were contributing to the same spot. We just literally added the individual displacements. Why? Can we justify this? Yes, we can. Formally speaking, it's the linearity of the wave equation. What does that mean? But mathematically, it means that in the wave equation, the displacement, yes, its derivatives occurred, but it never was squared or anything. It was always linear. But let's write this more properly. What do we mean by this? So justification for this thing is that if I put a displacement, I must say d1 x of t solves the wave equation, right? So it means the laws of physics allow this to happen. Maybe it's a sine wave, maybe it's a combination of sine waves, maybe it's something else. And d2 x of t, some other function, solves the wave equation. Then the sum of those displacement also solves the wave equation. Then d total equals d1, and I should say this is of course also a function of x and t, d1 x and t plus d2 x and t. That also solves the wave equation. Now, of course, if the total is just the sum of two displacements, and this one is a function moving to the right on the string, this represents a function moving to left on the string, well, then where neither one of them is 0, they're going to add like we did, but where if they don't overlap, then it's, you know, just this one is the blue one, this one is the green one, different locations in space. It's just a combined string with two shapes on it, like we saw. This is the mathematical justification. Now I'm just stating this. Of course, you should prove this, right? So go and prove it. Right? And it's very straightforward. It really just uses the fact that the derivative of a sum is the sum of the derivatives. That's all you need to prove it. Right? You just plug this into the wave equation. Right? It disobeys the wave equation, disobeys the wave equation. You plug this in the left-hand side. You split up your second derivative into two second derivatives. Each one is equal to part of its own right-hand side of the wave equation. So the combination is going to satisfy the wave equation. Very simple, but conceptually very important. All right, so that in a nutshell is the principle of superposition, and everything else is about applying it. So then, to give you a roadmap of what lies ahead, let me just state some phenomena we're going to be studying over the next couple of weeks that are all ultimately down to having more than one wave going along string, going traveling through the air as sound or as light, and so on. The first one is going to be standing waves. Standing waves is going to be a sine wave traveling in one direction, identical sine wave going in the other direction. So mathematically, I'd have, you know, a sine kx minus omega t and an a sine kx plus omega t. Same speed, same wavelength, but opposite direction. What happens? Well, depending on the wavelength, interesting things might happen. Then we might look at two source interference. So here we matched, for example, I have two speakers. They each produce sound waves from different locations in space. So what is going to be the effect where more than one sound wave reaches me at the same time, especially if the sound waves produced are just simple single tones, essentially a sine wave. And this very similarly related phenomenon is the double slit experiment, which is where you shine a light at two slits in some kind of screen, and they're really, really close together, too small to see in this picture. But those two slits each sort of act like a source of light, a bit like this setup here, except those two sources are really, really, really close together, and I'm looking what their effect is somewhere far away over here. So it's kind of the two source interference with an extreme geometry, right? The distance becomes very tiny compared to how far away we are from those slits. we're going to look at beats. So beats are two sine waves traveling in the same direction, but this time they have got slightly different frequencies. One has a slightly longer wavelength than the other. What's going to happen there? And then a couple more. I mean, there are lots more. A lot of, all of wave motion ultimately comes down to understanding the principle of superposition. It's very, very fundamental. Like the linearity of the wave equation is very fundamental. But just here are some specific things we're going to study. Thin film interference. Why do you get the colors of a little bit of oil on the road? Like rainy day, some car dripped some oil. Why do you get these sort of rainbow colors show up? What's up with that? Or soap bubbles. Or the sort of anti-reflection thing that you get on glasses, right? Well, how does that work? All down to understanding the principle of superposition. Single slit diffraction patterns, a little bit like a double slit. We've got two tiny slits. If there's got one tiny slit, still things aren't quite what you perhaps expected would be. So let's study that more closely. Color vision, and specifically about like how do we see like non-rainbow colors like white or brown. How do those show up? Like what is it? Again, it's going to be we are perceiving a superposition of different frequency waves. And in timbre, the sound of different musical instruments ultimately is going to be down to not just having a single sine wave, but a bunch of different sine waves at different frequencies. Very different phenomena, very different situations, yet all of them at a very fundamental level rely on the fact that you got a string, send down a wave, send another wave. Well, if they're both there at the same time, you just add their displacement. It's gonna be fun. Thanks for watching.